Good morning. This is a quick video to tie together what we already know about gas laws and empirical formula. So let's suppose that we have a sample of a gas that we do not know its molecular or empirical formula, but we can find that using gas laws, and that's the example we're going to show here. So let's back all the way up to January of last year when we were talking about that empirical formula. And the definition of empirical formula, once again, is that it is the lowest whole number ratio of a compound. There's a poem that you can memorize to remember how to find the empirical formula. You might say this sounds familiar. The formula is percent to mass, mass to moles, divide by small, multiply till whole. So let's put this to use. Here's an example. Let's say we have a sample of a gas A. We put it through a mass spectrometer, and we found that that little sample contained 54.5% carbon, 9.1% hydrogen, and the rest oxygen. So let's first remind ourselves how to find that empirical formula. So, percent to mass. We're going to assume we have 100 grams of that sample. So, 54.5%. If we assume we have 100 grams, well, that will just translate to 54.5 grams of it out of 100. Same here with the hydrogen. If I have 9.1% hydrogen, it'll go to 9.1 grams of hydrogen. Put our symbols here like that. And the remainder oxygen. So I'll say 100 minus the 54.5 minus the 9.1. And the remainder, that's oxygen, is going to be about 36%. Let me double check that. I think it is. 100 minus 54.5 minus 9.1, 36.4%. So, 36.4%. So if I have 36.4%, translating would be 36.4 grams of oxygen. Okay, percent to mass, first line of poem, boom, done. Next thing I'm going to do is mass to moles. So that's where I'm going to use that molar mass that's on the periodic table. I'm going to multiply carbon times 1 mole over 12 grams. Again, that 12 grams comes directly off your periodic table. Hydrogen, I'm going to do 1 mole over 1 gram. And oxygen, I'm going to do 1 mole over 16 grams. So, dividing all of that out, I find out that I will have 4.54 moles of carbon. I'm going to find out I'm going to have 9.1 moles of hydrogen, and I'm going to have 2.275 moles of oxygen. Quick note about sig figs. You don't have to use them in this problem because we are going to pretend that these are all literature values. Now, granted, if I'm looking at these percentages, I have a 3 sig fig number and a 2 sig fig number. I'm not going to worry about that today because I've got just computations with molar masses from the periodic table. So, second line of the poem done, mass to moles. We're on to divide by small. So I'm going to find the smallest number of moles, which is 2.275 for the oxygen. Divide everything here by 2.275. And that's just going to give me the ratio in terms of oxygens to every other element. So when I divide 4.54 by 2.275, I get really, really, really close to 2. And when I put it in my calculator, it was 1.9998 or something like that, so definitely round up to 2 in this case. When I put this in my calculator, I get 4, and of course here, 1. So ta-da! We've got our empirical formula. We don't need to use the last line of the poem, multiply till whole, because I already have whole numbers here. If one of these numbers was not a whole number, like it was 2.5 instead of 2, then I would have to do my last step of the poem. But for today, we're just going to say we've got an empirical formula of C4H8O. So that's my first example, using the percentages of the sample to get the empirical formula. Let's tie this now back into gas. Okay, tying this back into gas laws here. Same sample of gas, 0.23 grams of sample A. I didn't type grams there, but I'm going to put it there. When vaporized, had a volume of 0.0785 cubic decimeters at 95 degrees Celsius and 102 kPa. We're going to need to find the molecular mass of the sample. Now, remember that molecular mass is not the lowest whole number ratio of a compound. So we're going to get that molecular mass by using PVnRT. Because I've got a pressure, I've got a volume, I've got a number of moles that I can get from grams, I know my universal gas constant, and I've got a temperature. And here's where I could find those here. That's my little mass that I can get moles from. There's my volume, there's my temperature, and there's my pressure. I also want to remind myself that the number of moles can be found by taking the mass of the sample and divided that by the molecular mass, which is capital M lower subscript r. Otherwise saying little m over big capital MR. So I'm going to substitute that new expression into PVnRT. Just like that. And so I'm going to rearrange the PVnRT equation so that I isolate molecular mass. So this will turn into PV equals little m RT all over capital MR. I'm going to then multiply both sides by capital MR, the molecular mass, which is what I'm trying to solve for. And then the last thing I'm going to do is divide both sides by PV. So this will leave me with the molecular mass is going to be the mass of the sample times the universal gas constant times temperature, all divided by pressure times volume. I've isolated my variable, so now it is time to fill in my data. So my mass is going to be 0.230. 8.31 is my universal gas constant. Temperature has to be in kelvins. So I'm going to say over here, 273 plus 95 to get my kelvins, and that's going to get me 368. So that's my temperature, 368 kelvins, all divided by my pressure of 102 and my volume of 0.0785. So all throughout this, I've got 3 sig figs because all of my measurements have 3 sig figs. So rounding is really easy in this case. And when I solve this all out, what I should get is an answer of 87.8 grams per mole. And I could prove to myself what my units are going to be, because this is grams. This is going to be a universal unit that's going to cancel out everything except grams per mole. That's going to be temperature, that's going to be pressure, and that's going to be liters, kPa, L, and everything in that universal gas constant will cancel out those units. So that is my molecular mass of this sample A. From that information, we will then be able to get its molecular formula. And that's what we're going to do next. Okay, so let's put this these two pieces together to get my molecular formula, or the not lowest whole number ratio of that formula. Here's my empirical formula from example 1. Here is my molecular mass from example 2. First thing I want to do is find the molecular mass of my empirical formula. So I'm going to say here I've got 2 carbons at 12, I got 4 hydrogens at 1, I got 1 oxygen at 16, so I'll have 24 plus 4 plus 16 gives me a total of 44 grams per mole. Rounding is such a nice thing with these problems because they're mostly all lit values. If you notice here, that is really doggone close to 88 grams per mole. So I'll notice here that 88 grams per mole divided by 44 grams gives me a ratio of 2. So that's just going to mean that in my molecular formula, I'm going to double the amount of each one of those elements. So my new molecular formula will be C4H8O2. So now I know the molecular composition of that particular sample of gas that I have put through the mass spectrometer and want to find the identity. I'm going to do one last step. I'm going to go way back to the fall and see if we can remember how to do a Lewis structure for this. We're going to take this molecular formula and draw one possible configuration of that Lewis structure, which is called an isomer. Remember that an isomer is one possible configuration of a molecular formula, or an empirical formula for that matter. You might remember back from the fall the phrase HONK, 1, 2, 3, 4, which means that hydrogens always have one bond, hydrogens have one bond, oxygens will always have 2 bonds, nitrogens will always have 3 bonds, and carbons will always have 4 bonds. So I start with carbons in this case, and I'm going to just draw out my 4 carbons. I'm going to make sure all 4 carbons have 4 bonds. Just throwing on there some single bonds for the moment. And I'm going to start filling up my hydrogens. I need 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then I've got 2 oxygens. So I'm going to throw an oxygen here and an oxygen here. But we got a little bit of a problem because according to HONK 1, 2, 3, 4, oxygens need 2 bonds. So in order to fix that, what I'm going to go ahead and do is I am going to remove the hydrogen from this carbon. I am going to double bond the oxygen. Remember, oxygens love to be double bonded. And then I'm going to make a second bond on this oxygen by throwing the hydrogen there. Now everybody has adhered to the HONK rule. Carbon still has 1, 2, 3, 4 bonds. Oxygen has 2. Hydrogens all have 1. I could be particular. Remember that everything wants to be surrounded by 8 valence electrons, and I could say, oh, there's some valence electrons there, some valence electrons there, and there is one possible configuration for the C4H8O2 molecule. Is it the only one? Nope, but that's the one we're going to stick with today. Totally possible I could have oxygens here, totally possible I could have oxygens here. You could play around with it and you would have multiple different answers, which would tie into what we're going to be doing with organic coming up very soon. So hopefully this made sense to you. We will talk soon.